This week's lectures are particularly difficult because we are going to introduce on how spatial information is encoded by magnetic resonance imaging. And as you will see, this is done slightly differently than the X-ray imaging techniques. First, however, I want to start out with a recap of what we know about magnetic resonance. We have so far had introduced the static magnetic field. The static magnetic field, which is always called B0, it is necessary to create the equilibrium magnetization. So as you enter the magnet, you will build up a nuclear magnetization. That's this equilibrium magnetization. We're typically talking about field strengths of 0.1 to 12 Tesla. As a reference here, you have the Earth's magnetic field, which is, as you can see, much smaller than the fields used for MRI. Then what we do is this static magnetization, the equilibrium magnetization we've seen is not very interesting, produces no signal. So what we need to do is to excite the magnetization, that is, flip the magnetization into the transverse plane, and this is done using a radio frequency field, which is applied at the Larmor frequency. The radio frequency field is always denoted B1. It typically has a magnitude of 0.05 millitesla, and it is applied on resonance. So this is compared to, if you compare this to B0 in the order of Tesla, here we're on the order of millitesla. There's a considerable difference between the two. After the excitation with the RF field, we have the magnetization in transverse plane, and then this signal is being recorded. This we have introduced last week. This is known as the free induction decay. We have seen that after this excitation, we are no longer at thermodynamic equilibrium. We have to get back to thermodynamic equilibrium. This is done by relaxation, T1 and T2, or T2 and T1. T2 describes the decay of the transverse magnetization MXY, and T1 the return to equilibrium of the Z magnetization MZ. So the detection of the signal, the FID, that is done also with the RF coils. So both the excitation, the production of the B1, the radio frequency field, and the detection of the signal is done with the same piece of hardware. So this is what we've had so far with magnetic resonance. We have seen that the RF coils are used to measure the signal from the entire body. We have not introduced, therefore, as such, a spatial information. The means of detecting the signal is done by observing the precessional frequency, which is the Larmor frequency given by gamma B0 under the influence of a static magnetic field. And we have seen last week, this gives us also additional chemical information. Okay, so now how do we encode the spatial information? How do we get spatial information into our observation of the signal? And here the key is, let's suppose that we have the magnetic field, which is along Z, the B0 field, and we'll add a small field that varies linearly with space. So that's the Gx times X term here. So now this field, magnetic field, varies along X. What happens now? What we now have is that the Larmor frequency becomes a linear function in position. So if we write the magnetic field along Z and we produce it to vary spatially with X, Y, and Z, this spatial variation we can define as the derivative of the Z component of the magnetic field. Remember, static field is always along Z. With respect to position X, with respect to position Y, with respect to position Z, each of those derivatives are the components of a vector that we shall call G here. So, in general terms, then we have the static magnetic field as a function of position is given by the static field, B0, plus this linear term, and here it's a scalar product of G times R. This is, in all generality, the description of the magnetic field now. So for this case that we had here on the left, we used the vector G that was equal to Gx, 0. So just along X that we had a spatial variation. So if you look at along X, here's the X-axis, the magnetic field starts from the center point B0 and varies linearly around the position 0. Here we have taken the rotating frame representation, so at center there is no magnetic field. Along Y, so here's the Y-axis, we have a linear variation. And finally, along Z, we have the Z component of the magnetization along Z that increases in opposite directions. So now this vector G, we call this the gradient field. And the question is, how is this gradient field actually physically generated? I'll recap here the definition. The gradient vector is given by the derivative of the Z component of the magnetic field with respect to the position in each of the directions. That gives the components of this vector. To give you an idea what we're talking about here, this gradient field is typically on the order of 10 to 50 millitesla per meter, and it can be switched in a time scale that's typically on the order of 100 microseconds. And this is used to determine the spatial position of the signal, as we have seen from the Larmor frequency. So how is this gradient field generated? It is actually generated by a set of 3 additional coils. They're so-called gradient coil. So these 3 additional coils, they are put into 1 additional coil, and that's the gradient coil. So what we have here in green is the Z coil that produces the linear field in Z. In red, a linear variation of BZ along X, and in yellow along Y. In blue here you have also the RF coil indicated, and the subject is now lying here in this scheme inside the magnet. So to give us an idea how this is achieved, we'll take the Z gradient coil principle, just to give you an idea of how this is done, and we'll use the Helmholtz pair here. So what we have first, we have a ring current that's rotating in this sense counterclockwise. And then at a certain distance we have a ring current of the same structure, same diameter, but now the current is rotating in the opposite direction. The B0 is along Z, so it's in this direction parallel to the axis of the 2 coils. From Biot-Savart we can calculate, given the current in the yellow and in the orange and red coil, we can calculate exactly the magnetic field that's being produced. I'll just recap here the law for completeness sake, but we'll just take a very qualitative argument here, and basically we'll now draw here at the exact center between these 2 coils the magnetic field generated by the orange coil. That's the magnetic field indicated in orange, and by the red coil it's indicated in red. And now if we go along in at the axis, center of the axis, we'll move in this direction and in this direction. So if we move upwards, the field from the orange coil increases, the opposing field generated by the red coil decreases, so the magnetic field increases in this direction. Here at the center, for symmetry reasons, the 2 magnetic fields generated by the 2 coils are equal in magnitude but opposed, so it is 0. And if you go downwards in the direction of the red coil, we have the contribution from the red coil that increases and the contribution from the orange coil that decreases. And that in the end, in this situation, generates a more or less linearly varying magnetic field along Z, and this is the Z component. So what does this look in practice? In practice, one has a former, and then the coils are wound in copper on top of this former here. So this is a coil that corresponds to the X coil. Here is a single gradient coil that we have here on this structure. If we look at the complete gradient coil, then we have the complete structure, all the coils wound on top of each other. You can see here this Z gradient is produced a bit more complex than we have introduced. Note that the Y gradient and the X gradient, these 2, they are, from construction-wise, they are identical, except one is the rotated version of the other, rotated by 90 degrees. So here are the 3 gradient coils. Now, have you been in an MRI scan? Have you been a volunteer, or do you know of someone of a volunteer? Well, if you haven't been a volunteer, you might have heard that MRI scans are loud. And why are they so loud? We'll go after this question with the following 3 experiments that illustrate the basic principle that's behind the generation of sound during an MRI scan. Okay, in this experiment we have a permanent magnet here, and we'll be running a current through this structure here. And I will turn on the current and it will invert its polarity, and you can see the force that the magnetic field exerts on the conducting structure. First in this way, it's attracted towards the right. And now if I reverse the polarity, it is pushed in the other direction. That's a demonstration of the Lorentz force that's exerted on the structure that carries the current. This is what we have also in the MRI experiment. Okay, so in this experiment we have a coil here. I'll be pushing this button here, and this will introduce a magnetic field rapidly. This magnetic field induces a change in flux. This flux will induce eddy currents in this aluminum ring, which in turn, those currents through the Lorentz force will interact with the magnetic field of the coil, which will push back the ring, and the ring will fly upwards. So I will go 3, 2, 1, and here we go. If the ring is cut and cannot flow, I'll do the same experiment here. So now we have no ring current, so there is no current that can flow. Push the button and nothing happens. Conversely, if I run an AC current through the coil here, then I have a change in magnetic flux, and as I increase the current, that is the change in magnetic flux, then the force increases that is acting on the ring. Okay, so in this experiment what we're going to demonstrate here is again the Lorentz force. We have a coil here, and there's a big capacitor underneath. This capacitor will be charged. This will take some time, and then I will release the charges stored in the capacitor. This creates a surge of current in here, which creates an enormous flux change through this coil, which in turn induces eddy currents in the Coke can, which through the Lorentz force will contract and be split in 2. So we will now start charging, and this process takes a while. We can see over here on the dial the increase. We have to charge to roughly 10 kilovolts. Okay, so we have reached the steady state. 3, 2, 1. And now if you touch this, you can feel that it is actually quite hot. So here in this video is a practical example. So we can hear the scanner as it is going, and you hear bzz, 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 bzz. That's the typical sound of an MRI experiment under progress. So where does this sound come from in the MRI scanner? And the thing here is that, as we've seen with the experiments, we're looking at the Lorentz force of the B0 field, let's say it's 3 Tesla, so it's a very strong magnetic field, on rapidly switched current in the gradient coil. So this force builds up. Because the current in the gradient coil is switched rapidly, the force builds up rapidly, and this is like a hammer knocking on a structure. Here it's the copper structure that hammers on its support. The support doesn't move, like if you hammer on a table, like this table here. The support cannot move, but you still have this knocking sound, and that produces very strong forces. The examples with the Coke can are just mere illustrations of the kinds of forces that are in there. And so, to give you an idea what we're talking about here, one switch is typically 100 amperes in about 100 microseconds. That's the kind of forces that we're looking at. Now, without means engineering attempts to reduce the sound inside the scanner, it would be much louder, and over the years the scanners have become considerably quieter than they used to be 10-15 years ago. So there's continuous research going on and development in trying to reduce the noise. But in general, it is advised to go into an MRI scan with the earplugs so that one does not have some unpleasant surprises. Now, before going into how the image is reconstructed, I want to illustrate here with a simple example. I want to illustrate how slice selection is achieved. So we have seen in the previous two courses that the radio frequency field B1, which is applied at a frequency omega RF, it is capable of exciting the magnetization into the transverse plane if omega RF matches the Larmor frequency of the precession of the magnetization. So if omega RF is equals to omega L, then one is capable of flipping the magnetization into the transverse plane. What we're looking at here now is a cube. You can consider this an object, part of an object. It's a 7 by 7 by 4 matrix, and each of these voxels contains the magnetization vector. We have the z direction here, we have the x direction, and we have the direction in y. Now we'll consider that we are here and that we have a position z0 that corresponds to the gray voxels here in our object, and we consider that the Larmor frequency at this position is given by gamma b0 plus gamma gz times z0. So the Larmor frequency is equals to that, and if we set the omega RF equals to that Larmor frequency, then we are capable of flipping the magnetization into the transverse plane. This is done on resonance, as we have seen that the magnetization that is off resonance, that is that precesses, is not touched by the RF pulse, by the B1 field, but only those who are on resonance. So in our rotating frame, which is always set to the frequency of the B1 field, this magnetization can be flipped into the transverse plane. So in this case, we can see that the magnetization that corresponds to the gray voxels, applying an RF field with this condition, will flip the magnetization into transverse plane for all the gray voxels, and the others are untouched. And then it becomes a simple means of changing the frequency of the synthesizer to change the frequency of the RF field, and that alters the position of the slice. So here's now in the rotating reference frame, so this term does not appear. The omega RF is equals gamma gz times z, and then we select in our object this slice here. And now if we change the frequency of the synthesizer, we will change the position of the slice, and as we see here in this animation, it moves up and down with position as we change the frequency. Here I would like to make a side point, and that is, which is important, we should not confuse two things. Typically we refer to x and y to the positions in space, in real space. So z is this direction, x is typically this direction, and y is typically this direction. mxy or m perpendicular refers to the transverse magnetization. Here x and y denote the transverse components in magnetization space. So this is different than the real space. If we put ourselves into a rotating reference frame, we do that in magnetization space and not in real space, and we're dealing here with two different coordinate systems. However, they do share the z component. So this is important that we keep that in mind for the rest of this course.